Okay, so the final paper in the session, which is, I should mention, is a distinguished paper, is automatic parallelism management, and Sam Westrick will give the presentation.
Great. Thanks, John. So my name is Sam Westrick. I'm a postdoc at Carnegie Mellon University. This is joint work with Matthew Fluet from Rochester, and as well as Mike and Umut, both from Carnegie Mellon. So the setting for this work is a style of parallelism that we refer to as fine-grained task parallelism, and more specifically, fine-grained fork-join parallelism. And we have this function par, which I have the privilege of, everybody has already introduced this for me in the previous talk. So par lets you run two functions in parallel and get back their results as a tuple. Okay? And we rely on a scheduler under the hood to guarantee efficient execution on any number of processors. So you can run it on one processor or 100 processors, and it will scale appropriately. Okay? I've just drawn a little example here. Here's a piece of code you might write in this style. This is a parallel for loop where it takes a function called body. That's the body of the loop, intuitively, all right? And it takes a loop range, an index range, low to high, and it's going to execute the body in parallel for every index in that range. Okay? And you'll notice that this is very fine-grained in the sense that individual units of parallelism in this particular piece of code are going to be individual calls to the function body. Okay? So we, let me just briefly say, the parallelization strategy here is, okay, we divide the range in two, and then we recursively process the two halves of the range in parallel. And in order to do that, we call this function par. Okay? There's immediately a problem, though. Parallelism is not free, and in particular, that function par, which can evaluate two things in parallel for us, is not magic. Under the hood, it does something. What does it do? It probably allocates a little closure to describe the task, and it stores that in a scheduler queue. Right? That's a non-zero cost. It's actually a fairly modest cost if you really look at the low-level details in terms of number of processor cycles that you're going to need. Okay? So if you take that piece of code, that very fine-grained parallel for loop, and you compare it against this alternative implementation. And what I've done in this implementation is I've cut off the parallelism below a threshold. And that threshold is what we call the grain size. And that's something that you could imagine if you're writing this code, you could choose that. You could even hard code it if you'd like. So you could say, below a loop range of 1,000, don't call par anymore, right? If you run these two pieces of code and imagine giving it some reasonable loop body, I don't know, you can easily get a factor 50x performance overhead for the top version. The fine-grained one could be 50x slower than the bottom one. And we'll actually see some performance results later. Okay? This is because of the overhead of par, which on its own might seem like a small overhead. But if you call par 1 billion times, or you attempt to call par 1 billion times in a short period of time, it will be 50 times slower than you expect, or maybe even 100 times slower. Okay? This is broadly known as the granularity control problem. Okay, and there's this question of how much parallelism should I expose as a programmer when I'm writing my code? Okay, how fine-grained should I make my parallel tasks? This is a question which we argue is fundamentally incompatible with higher order programming. Okay, because in this example, I have this loop body that I can pass in as a function argument, and I can instantiate it for anything. Okay, maybe I call it 1,000 times with a very expensive function. And in this case, you probably want a very small grain size because you want to expose the maximum amount of parallelism. But maybe you call it 1 billion times with a very cheap function. And in this case, you want a grain size which is much larger, potentially even 1,000 invocations or 10,000 invocations of your loop body. Okay? And now it can get even wilder, right? You could have nested parallel for loops. Perhaps this could even be data dependent. So the sizes of the inner loops could be wildly different from each other, and that could be something which is input dependent, which changes depending on what input you pass to the program. Okay? Like some sort of nested parallel loop over a jagged array. Okay? So clearly, we should be starting to think, like, can't we automate this? This seems like something that not only is it going to be terribly difficult to do as a programmer, to tune all of these grain sizes, okay? But it's not something which is portable across machines. You might need different grain sizes in different machines. There's tons of problems here. And indeed, there is tons of existing work on this problem. We just listed a few examples here. But as far as we know, none of the existing solutions can get us these three goals that we want. We want something which is a fully general solution. We want something which is provably efficient. And what I mean by that is that even in the worst case, it's not too bad, right? And actually a guarantee by the language implementation that it won't be too bad. And we want something that's actually implementable and effective in practice. Now, let me just call out to a particular piece of prior work that some of my co-authors did, as well as some of the members of this community. It's called heartbeat scheduling. And this proposed a technique for getting provable efficiency, okay, and a fully general solution. But they did not show how to actually compile for it for real. So in some sense, this paper that I'm presenting for you today is a spiritual successor of the heartbeat scheduling work, where we figured out how to actually compile for this technique and actually implement it in a real compiler. So we call this automatic parallelism management, and it consists of two components. We have like a static element and a dynamic element. So statically, we expect the programmer, we say, programmer, please feel free to use par very liberally to express opportunities for parallelism, and don't worry so much about this granularity control problem, okay? The key to making this work and be efficient is that we need to be able to compile this par function into something which is nearly zero cost, okay? And the technique that we develop in this work is it's a compilation technique. It's really a calling convention, a low-level calling convention. We call it PCall, which enables this nearly zero-cost par, and we'll see that in a moment. One really interesting thing about PCall is that it can be dynamically promoted into an actual parallel task, but by default, it exposes no parallelism. So the default behavior is going to be a fast sequential execution, but then during execution, we can convert that into real parallelism. So that brings me to the dynamic element of this work. What we give is a provably efficient scheduling algorithm for these promotions. And each promotion is going to release some parallelism by creating a task, but it also is going to incur a cost. So there's a clear trade-off that we have to be very careful with here. So we give an algorithm which guarantees these two properties, work efficiency and span efficiency. And if you're not familiar with the work span model, I'll just say, basically, these preserve the asymptotic behaviors of your program, guaranteeing that it doesn't have much overhead, and also that the theoretical amount of parallelism in your program is preserved. And a key contribution of this work, as I mentioned, is that we have a full implementation of this. It's currently in a branch of Maple that you could play with today, and we're working on integrating it into mainline Maple, and it should be released soon as a new version of Maple. So just brief overview of how this works. This is the compilation pipeline for the Maple compiler, and Maple is based on Milton, for those of you who are familiar with Milton. And our main contributions are kind of in the middle and at the end. So in the middle, in an SSA intermediate representation, we introduce this PCall calling convention that I'll get to in just a moment. And then down at the bottom, we actually, at runtime, schedule these promotions dynamically in a provably efficient way. So how does PCall work? Well, let me begin with, on the left, an illustration of kind of a standard calling convention where, in this example, we're growing downwards. So in a standard calling convention, you push a return address onto the stack, which encodes where the caller should resume when it resumes. Okay? PCall is very similar, but we use two additional return addresses. So I can now very clearly define what I mean by nearly zero cost. The nearly zero cost element of our implementation is that it's a sequential function call at the low-level sense of a sequential function call with two additional return addresses. So two additional stack slots. That's the cost that we're paying. Okay? Now, I'm going to get, in a moment, to explain what these two additional return addresses are for. But I just want to point out that this is compatible with the existing calling convention. And in particular, if you don't touch it and you don't promote it, then the default behavior is going to be a sequential execution. So the idea here is that you're going to start calling a function, and then that function will return to this retseek return address, and that code path can just be the rest of the sequential execution. So by default, we can get a sequential execution out of this calling convention. But what we can also get from it is parallel behavior, and that's what the two additional return addresses are used for. So in order to promote one of these, we essentially have access to two different alternative code paths that we could take. One of them is for a new task, and the other one is for synchronizing with that new task. So in order to promote PCall, so by the way, this is like buried in our call stack, and you could have a thread which is currently executing a function call which is 100 function calls deep, right? You might be deep in your call stack. You go back and you find an outstanding PCall in your call stack, and you can do a promotion on it. And this will release some amount of parallelism that was previously locked away in your call stack. Okay? So we actually adjust dynamically the behavior of the continuation of the caller. So when we get back to the caller will resume at a different place than it originally expected to. Originally, it would expect to resume at retseek. Instead, it goes to retsync. And retsync, we can use that to give it a code path which will synchronize with the new task. And in particular, in order to do that, we also have to store a pointer to the new task, and we put that in the other, in one of the extra slots that we were using for this technique anyway. So we don't need another additional slot for this additional pointer. Okay? And then that other return, the other return address, ret spawn, we use that to specify what code the new task should run. And it's kind of cool. The new task the new task feels like it is resuming as the caller. Like from its perspective, it's as though it's resuming as the caller. And so it has access to all of the local vars of the local variables of the caller, because we actually just copy the whole stack frame. Okay? But it's as though it kind of resumed without getting any return value from the function call. So that's the compilation technique, and now I just need to tell you about the algorithm for actually scheduling promotions in order to get provable efficiency. Okay? So as I mentioned, each promotion exposes some parallelism, but it incurs a cost when it does so. And our idea is basically to amortize the cost of promotion against the true work of the computation. And this idea comes from heartbeat scheduling, and this is the place where we're taking that heartbeat scheduling idea and really applying it to this work. Now, the algorithm we actually use in this work is a little bit different than the heartbeat algorithm, but here's the idea. Every n microseconds, and I'm measuring this in microseconds because this is really, we're talking about fairly small granularities here. You are going to send a signal to every thread in your system, and you're going to give that thread some number of tokens. And the idea is that these tokens are amortization tokens. So the algorithm is very explicitly amortized. Okay? And the idea is that you can spend one token to perform one promotion. Now, there's a really interesting detail here, which is that if a thread performs a promotion, it has to always promote the oldest thing, the thing that's buried deepest above it in the call stack. This is for span efficiency. Okay, so let me just mention we get work efficiency and span efficiency, and those are in the paper, and you can look over those if you're curious. The span efficiency result critically relies on this outermost parallelism. This is an insight also from heartbeat scheduling. I can give you some intuition for it, which is that the oldest piece of potential parallelism that's locked away has suffered the longest delay, or it is potentially the one that has suffered the longest delay, and therefore it is most likely to be on the critical path, and therefore needs to be exposed as parallelism as soon as possible. That's kind of my own intuition for it. But you can see the theorems for the actual proofs. So how about some experimental results? So we did a fairly thorough evaluation in the paper. And what we're looking at here is a measure of the overhead of parallelism in the worst case. In the worst case here, I mean like turn off granularity control and run your super fine-grained parallel for loops like we were looking at earlier in the talk. Okay? So what we do here is we look at two versions of the same program, one with granularity control turned off and one with manual granularity control where we've gone in and make sure that we get best performance by tuning those grain sizes. So if you look at the ratio of the performance of those two, you can get some sort of sense of the overhead of parallelism. What was the overhead that I paid in order to create these fine-grained tasks and schedule them, okay? And you can see in the worst case, we actually found an example where we can get 46x slowdown if we turn off granularity control. But with the new techniques, we make that much better. We bring it down to, in a worst case, of say only 2x or 3x. There's one example, so I'll just mention these results are on 64 cores. And the kind of speedups that we're getting on 64 cores are comparable to what you would get with manual granularity control as well. So we're getting really good results, and I think we've shown that it's really effective in practice. There's more empirical results in the paper where we do more thorough evaluation than what I have time to go over here. Anyway, I think this has demonstrated that we're really getting something which is working quite well. So just a summary of this technique. So it's a nearly zero-cost compilation technique for this par function. And I can summarize that approximately as it's this p-call calling convention together with dynamic promotions, and in particular, a provably efficient algorithm for dynamic promotion. What we're able to get from this is both provable efficiency as well as practical efficiency, even if you are totally not careful with your granularity control. The guarantee we give you is that if you're not careful, it won't be necessarily as fast as it could be, but it won't be too bad either, right? Maybe you could expect 2x overhead, 3x overhead. In the worst case, maybe 5x overhead, but definitely not 50x and definitely not 100x, okay? So we have a lot more in the paper. We give a full formalism for this SSA intermediate representation where the p-call calling convention becomes important. And we give a semantics to PCall through the means of that, through the means of an operational semantics for an SSA intermediate language. Okay? We have the theorems of the work and span efficiency. We have a fairly in-depth description of the changes that we made to the compiler in order to make this happen. And in particular, Matthew Fluet helped with changing the compiler, and he's intimately familiar with how the Milton compiler works, and that's the compiler that all of this work is based on. And for Matthew, granted, he is an expert at this particular compiler, but he was able to implement all of this in essentially like 1 or 2 weeks. So it actually wasn't that bad in that sense. And as I mentioned, we have an in-depth empirical evaluation. There's, actually, I didn't even write it in the list, but there's quite a bit more. So Matthew worked on the compilation aspect, and I worked on mostly the scheduling and runtime aspect, and we had to integrate it with the garbage collector, and there's some nuances here. And the scheduling is also, there's some interesting integrations with the scheduler, and in particular, the clone optimization. If anybody's familiar with the clone optimization from the Silk work, that integrates seamlessly with this approach. And you end up with kind of like 3 different runtime representations for tasks that have increasing cost that you kind of like move through. Like the first one is promotion, and the next one is the clone optimization, and the third one is actually creating a full thread. Anyway, lots of nice implementation details. So I hope you'll read the paper, and I hope you'll check out our work on Maple on GitHub, and happy to take any questions. Thank you.
Hey, awesome talk. So in the interest that good is never enough, there's still overhead, right?
Yes.
Between the between the red line and the dotted black line. So what's your best explanation for why there's still overhead, as well as is that overhead fundamental to your approach, or could it be improved with more engineering?
Yeah, a fantastic question. Okay, so the overhead, what is the overhead? So I say nearly zero cost implementation of PAR. It's still not zero. And getting it down all the way to zero might, maybe we're approaching the limits of what's possible at this point in terms of implementing PAR efficiently. So why is it not all the way, why is there still some overhead? Well, you have to implement, in this technique, you have to implement PAR in terms of an actual function call. That's a non-zero number of instructions. And if you compare that against the most fine-grained thing you could possibly imagine, like a PAR that on the left-hand side does a single addition, and on the right-hand side does a single addition, maybe, the cost of the PAR is still going to be more than the cost of those 2 pieces, right? So I think there's something, we're getting close, I think, to the limitations of just using PAR alone, and I think to fix that, what we probably would want to have is, say, a parallel for loop as a primitive in the language. And my co-author, Mike Rainey, has currently been working on developing compilation techniques for doing some of these similar techniques, but for nested parallel loops and automatically getting good automatic parallelism management essentially for nested parallel loops. So I think wait another year or 2, and maybe we'll have it in Maple also.
Awesome.
Yeah, thanks. Awesome talk. So I was wondering, where do you actually do the promotions? What triggers a promotion?
Excellent. So the mechanism that's going on here, we have a signal handler, so there's a signal delivery mechanism and a signal handler. So there's a signal delivery mechanism, which for this particular work, we actually got away with using an interrupt timer on Linux, and we set it to deliver a signal every 500 microseconds. So every 500 microseconds, that's one opportunity for a promotion. And what happens is each thread responds with a signal handler, and in the signal handler will decide whether or not it wants to do a promotion right now. There's a second time that promotion happens, though, and this is one more element of the overhead of PAR that we were just talking about with Will's question. We actually check at each PAR if there's an opportunity to spend a token. And so that's a small conditional that we've put on each PAR. That's another opportunity for promotion. But that's actually key to some of the performance results we're getting here. In particular, the Delani benchmark was one where before we did this, we got like a 3x slowdown, and we were able to bring that down to essentially matching the performance of the manual granularity control. This was basically the delay between creating parallelism and then releasing that parallelism was stacking up in order to actually be measurable on the impact. And so we created this mechanism where you actually eagerly promote in the case where you happen to have a token in hand already. And that's another place where we actually trigger promotions. Yeah.
Doesn't using Unix signals have significant overhead?
That's a great question. I think we found that if we have a large enough interval for our signals, that the overhead is not too bad. We're doing some tricks here. If you use a very large number of processors, then we actually designate one of the processors as a signal relayer, and that processor essentially becomes, its only responsibility is to deliver signals. It elects itself as like the signal giver. And this helps speed up things quite a bit.
Fascinating.
Yeah.
Hello, really good talk. I was just wondering, is there a way that this could be integrated with compiler frameworks like, maybe LLVM or MLIR or something like that? Like, what would that look like? Like, would it be similar to like their GC integration, where like they'd have a new calling convention and then you integrate it with some runtime, or what?
Yeah. Unfortunately, I'm not super familiar with LLVM, so I won't be able to give you a great answer, but I can give you an okay answer, which is that if they have support for calling conventions, such as like installing additional return points, then it's really not that far off. Like that's really, what we needed to do was, we needed to tell the compiler about these 2 additional return addresses, and in particular, you have to do like any sort of flow analysis for optimizations, has to consider those potential return points. It's almost like you can think about it as a non-deterministic conditional. It's like you can think about it as, I don't know which one I return to.
Oh, okay, so you need support for multiple returns then?
Yes, you do.
And we actually treat them as like exceptions?
It's similar. I think it is similar to exceptions, and it's possible that you could. By the way, I originally tried to implement this with exceptions. I was trying to use exceptions as a hack in order to do like multiple returns. It didn't end up really working, but I think there is in terms of overheads and stuff, right? But I think there is potential for like thinking about this as some sort of exception mechanism, right, with multiple return. Yeah.
It sort of looks like the C++ multiple return mechanism.
Yes.
And I, from my own experience with doing this stuff in LLVM, it would probably be really hard because it doesn't like things like multiple returns. There were some other people who had questions. I think. Frank?
Yeah, so any hope this might work with futures or only fork join?
I have some thoughts. I think it can, actually, and I've talked to Mike about this. Mike is one of my co-authors, Mike Rainey. I have an idea for how we could do it. Will it end up working out? We'll have to wait and see, but frankly, the more pressing challenge is probably the one that Stefan mentioned, which is we would have to implement futures first in Maple in order to really test it. So that would be the more pressing issue first. But honestly, I do think it can be done. Yeah, I'd be happy to talk about it afterwards. Yeah.
Yeah, so we have some Discord questions. I would just follow up with that. I think we did something similar to this in Manticore,
yeah.
and everything was implemented on top of futures in Manticore. So
perfect.
Maybe it would work.
Good.
So the first question is, could invoking the oldest P call have negative effects in terms of locality? If basically, I think with respect to things like cache effects.
It's an interesting question. This can absolutely have an effect on cache performance, and it's non-trivial what that impact can be. Let me just mention, though, that outermost parallelism actually is probably what you want for cache locality in most cases. Because the outermost parallelism, the typical case for like a parallel fork join computation is that the outermost parallelism is going to be encoding a huge task which is unrelated to your current computation. So it's going to be encoding some huge task which is like far away. Like maybe you could be accessing an array in parallel, and the outermost parallelism is going to be the other half of the array, which could be gigabytes away physically in memory. Versus innermost parallelism would be something that's very close to you. That's the thing that you want to keep local. And I think promoting outermost is really key to getting the good performance that we're getting here.
Okay, so I guess we're a little bit over time, but we can address a couple more questions. So could the Silk folks, or whoever does fine-grained fork join in C or C++ land, use your techniques?
I think so. So Silk has an interesting recent project. It's called Taper, and it's an LLVM integration. And they encode parallelism actually in a way that's not far off from some of the ideas in this paper. Their goals in that work were completely different. They were looking at the opportunity for doing better optimizations of parallel programs by encoding parallelism in the compiler in a smarter way. But that being said, I think it is possible that they could adapt those ideas to actually implement these techniques, but maybe they would run into some of the LLVM challenges that we were just talking about a minute ago.
Okay, well, I think that with that, we should conclude the session. Thank you.
Thank you.